Okay, so in this video, I'm going to talk about how we can figure out how fast the object is moving at any one time for one of these oscillators that we're talking about, either the mass spring systems or the pendulums. So we're talking about velocity this time around. So one thing that some people might be tempted to do when you're trying to figure out the velocity is to use kinematic equations, the equations that we talked about at the start of the year. But we can't use those kinematic equations here. And the reasons that we can't use those is because these only work if the acceleration is constant. But as we just saw in the last video, the acceleration is constantly changing for this object. So when the spring is fully stretched out, the acceleration is the maximum, but then as it crosses through the middle, it goes to zero. And so we aren't able to figure out what the speed is at any one point by using these kinematic equations, using what we know. You would have to use calculus in order to answer that. So instead, what we're going to do, we're going to use conservation of energy. And this makes our life much easier. And so we're going to start by looking at mass spring systems. And we're only going to be talking about horizontal ones here. You'll never see situations with a vertical mass spring system where you have to use conservation of energy. So don't worry about those. But so when we've got a horizontal mass spring system, the two types of energy that we have to worry about are, of course, kinetic energy, which has to do with motion. And then the other type of energy is, of course, potential energy. But it's specifically the spring potential energy that we're talking about here. So we're not going to have to worry about gravitational potential energy when we're talking about springs, because we're assuming it's horizontal, so there is no potential gravitational energy involved. 1/2 mv squared is how we calculate the kinetic energy. 1/2 kx squared is how we figure out the potential energy. So what's going to happen is that as our spring mass system, as it oscillates back and forth, what's going to happen is that the kinetic energy and the potential energy are going to be transformed into one another, back and forth and back and forth. So when you stretch an object fully out, let's say we stretch an object out some distance, x. Well, when it's fully stretched out, all that we're going to have is kinetic energy. All we're going to have is potential energy. When fully stretched, we only have potential energy. We've stored some energy in the spring, so when the object is fully stretched, we have no kinetic energy. And what does that mean? Well, that means that the velocity of the object is equal to 0 when it is fully stretched out. What about when we're at equilibrium? The equilibrium point. So in this case, it's not stretched out at all, which means that we have no potential energy. That means that we have only kinetic energy. And if we have only kinetic energy, then that means that V is a maximum. So this is a little bit different than when we were talking about acceleration, but as the object passes through its equilibrium point, it's going to be moving at its fastest speed, but it's going to be accelerating at its lowest amount. So they're kind of opposites of each other here, velocity and acceleration. And then in between the points, when it's not fully stretched out and it's not at the equilibrium point, what's going to happen? Well, we're going to have some amount of potential energy, some amount of kinetic energy, and we're going to be able to calculate all of these things. And we're going to look at an example in the next video. But just wanted to mention this. So the important points to consider here again is when fully stretched, we only have potential. When at the equilibrium point, we only have kinetic. So really, one way we can think about it is that the energy of the kinetic energy plus the potential spring energy at any one point is always going to be equal to the kinetic energy plus the spring energy at a second point. And so really you can always come back to this equation here. If you are at either the equilibrium point or at the extremes, then some of these values are going to be 0. And we're going to see that in the example. So that's with the mass spring systems. With pendulums, it works out to be something very similar here. Is that the two, though in this case, the two types of energy that we have, well, of course, we have kinetic energy of the object that is moving is going to be 1/2 mv squared. We're also going to have potential energy of gravity because the object is moving up and down a little bit, and we'll calculate this with mgh. So if we've got our pendulum, say here's our equilibrium point, it's been pulled off to the side by some amount. Let's say that's the path that this pendulum is going to take. Well, you can see that if we use right there sort of as our reference point, our object is moved up some height. And so at its most, at its biggest displacement, we only have potential energy and we have no kinetic energy. So this is very similar to the last situation. Anytime we have no kinetic energy, V is 0. And this potential energy is, of course, just going to be mgh. And then at equilibrium point, so as the pendulum passes right through this equilibrium point, right through the middle here, we are going to only have kinetic. Which is going to be 1/2 mv squared, and potential energy is 0 at that point. So at this point where we only have kinetic energy, again, our velocity is maximal, we'll say. Hopefully that makes sense. So we're going to look at a couple of other examples, like I said, in a second here. But again, you can think of the potential energy plus the kinetic energy at one situation. Say we could say that this is situation 1, this is situation 2, is going to be equal to the sum of the energy at the second situation. And so the extremes are the easiest positions to worry about because we only have one type of energy in those situations, but we can also figure out how fast it's going at any point in between. Okay, so in the next video, we're going to take a look at a couple of examples.